Hello everyone, myself Vinay Kumar M. I am actually pursuing PhD in physics. So in this particular YouTube channel, I will be teaching physics, chemistry and mathematics. So if you want to learn physics, chemistry and mathematics starting from 8th standard till 12th standard, then please do subscribe to my channel. Till now I was actually teaching the 8th standard science subject. So from this video I will be teaching 8th standard mathematics subject in English. So the first chapter in 8th standard maths chapter is rational numbers. We all know we count numbers starting from 1 till infinity, like 1, 2, 3, 4, 5, 6, 7. Like this we go up to infinite numbers. So these kind of number which has got started from 1 and it goes up to infinity is actually known as natural numbers. So here one thing you should remember, there should not be any kind of decimal numbers like 1.1 or 2.3 or 4.6. Like this number should not be there. So a full number should be there like 1, 2, 3, 4. Like this it should go up to infinity starting from 1. So these kind of numbers which starts from 1 and goes till infinity without any decimals in between. So such kind of numbers are actually known as natural numbers. So natural numbers. Now you might be wondering where the 0 has went. So if you add 0 to this natural numbers, then that particular natural numbers will become whole numbers. So here also it will go up to infinity. The thing is here 0 is also added. So if 0 is added in this natural numbers set, then that particular numbers are known as whole numbers. So the only difference between whole numbers and natural numbers is that whole numbers starts from 0 till infinity, natural numbers starts from 1 till infinity. Now you might be wondering what is behind 0, because we have started from 0, 1, 2, 3. Like this it goes up to infinity. What is there behind 0? The negative numbers of these positive numbers. The negative counterparts of the positive numbers will be there behind 0. So for example, it starts from minus 1. Actually after 0, before 0, it starts from minus 1 and again it goes till minus infinity. So minus 1, minus 2, minus 3 and it goes on. So just like we have positive numbers after 0, the same similar numbers will be the negative numbers behind 0. So starting from 0, it will go till infinity. Behind 0, before 0, it will start from minus 1 and again it will go till infinity. So you might be knowing number line. So on number line, 0 will be at the center position and after 0 there will be 1, 2, 3. Like this it will go up to infinity, and before 0 there will be minus 1, minus 2, minus 3 and again this will also go up to infinity. So these kind of numbers which contains both negative, positive and 0 along with it are known as integers. So these kind of numbers which contains both positive and negative numbers along with this 0, then it is known as integers. So here also you should remember that there should not be any decimal places. Like it should be the full whole number. It should not be 1.1, 2.2 like that. It should not be there. It should be a full whole number starting from 0 till infinity, and before 0 also negative numbers will also be there which will also go till infinity. So these kind of numbers are known as integers. So now you might be wondering that I am actually discussing about natural numbers, whole numbers and integers, but the heading of this particular chapter is rational numbers. So what do you mean by rational number? So any number which has the form of p by q is actually known as rational number. So any number which can be written in the form of p by q is actually a rational number. Here all natural numbers, all whole numbers, all integers can be known as rational numbers, because natural numbers starting from 1 it will end till infinity. So it doesn't have any ending. But this one can be written as 1 by 1 and this 2 can be written as 2 by 1 and this 3 can be written as 3 by 1. So if we are just writing a number like this 3, then in denominator there will be by default 1 will be there. So again any kind of natural numbers, or even if you consider a whole numbers, then also there will be 1 in the denominator. Even if you consider any integers, then also there will be 1 in the denominator. So all integers, all natural numbers, all whole numbers can be written in this particular form. They can be actually divided by 1, because if you divide by 1, again you will get the same answer, because 3 divided by 1 is again 3. So 3 can be written as 3 by 1. So if it is in the form of 3 by 1, then it is in the form of p by q. P by q means any number which is expressed in the form of numerator divided by denominator. So such kind of form if a number has, then such kind of numbers are known as rational numbers. So here any natural numbers, whole numbers, integers can be written in the form of p by q just by putting 1 in the denominator. Hence they can also be a rational number. So examples for rational number is that you can take 2 by 3, you can take 2 by 1, you can take 4 by 5, you can take 6 by 7, or you can take 100 by 1000. So any kind of number which can be put in the form of p by q can be the example for rational numbers. So now let us discuss the properties which are involved with these kind of numbers. So first property is closure property. So in this closure property you have 4 different kind of divisions. So one is closure property under addition. So the other is closure property under subtraction. The other is closure property of multiplication, and the last one is closure property under division. So now let us go on checking each set of numbers can obey closure property or not. So first let us take whole numbers, because whole numbers contains natural numbers also in it. So if we actually test for whole numbers, then it will automatically apply for natural numbers as well. So I am testing closure property for whole numbers. So let us take one example. Let's say 0 and 2. So 0 and 2 are whole numbers. So if we are actually testing the closure property of addition, then even after adding these two whole numbers, we should get a whole number after adding these two whole numbers. So then only it will get satisfied for closure property under addition. So for closure property under addition, so I'll be just writing here closure property under addition. The formula is a plus b if they are actually equal to c, then a if it is belonging to a set of number. Let's say now we are actually testing whole number, and if b also belongs to whole number, so this symbol is actually belonging to a certain kind of set. So now a is belonging to whole number, b is also belonging to whole number. Then after adding this a and b, the c should also belong to the whole number. So now here in place of a I am putting 0, and in place of b I am putting 2, because here I have considered 0 and 2 as my example. So now if I substitute 0 in the place of a and 0 in the place of 2 in the place of b, then 0 plus 2 will be 2. So here 0 is actually a whole number. So 2 is also actually a whole number. When we are adding two whole numbers, then again we are actually getting a whole number. So here we are getting 2. That is also a whole number. So here if you try with any whole numbers, if you take any whole numbers and add them together, then you will get another whole number only. Hence whole numbers will be obeying closure property of addition. So here I can write whole numbers will actually obey closure property of addition. Now let us check whether closure property under subtraction will be obeyed by these whole numbers or not. So now I am considering closure property of subtraction. So here also I will consider the same example 0 and 2. Now here the general formula will be a minus b is equal to c, because here we are actually doing the subtraction of two numbers. So even after doing subtraction, the number which we get should also belong to the same set. For example, if a is actually belonging to the whole number set and b is also belonging to the whole number set, then after subtracting a and b, then also the answer which you get should also belong to the whole number. So here let us say we are taking 0 and 2 as our example. So we substitute 0 in place of a, minus b, so here minus is there, in place of b we are substituting 2. So 0 minus 2 will be minus 2. Here actually 0 is whole number, 2 is actually whole number, but after subtracting this whole number with a whole number, we are not getting a whole number. This minus 2 is not whole number. So it is not a whole number. It is actually an integer. So negative numbers are not there in whole numbers, and it is not there, like negative numbers are not there in natural numbers as well. So natural numbers and whole numbers will never obey this particular closure property under subtraction. So whole numbers do not obey closure property of subtraction. Now let us check closure property under multiplication for this whole number. So closure property of multiplication, the next one is. So let us consider the same example 0 and 2 for this also. So here also, when you multiply two whole numbers, then the answer should also be a whole number. So here A should belong to whole number, B should belong to whole number, and if you are multiplying two whole numbers, then the answer which you get should also be a whole number. So let us say we are taking 0 as one number, and B in the place of B we are taking 2. So 0 into 2 will be 0. So here 0 is also whole number and 2 is also whole number. So when you actually multiply these two whole numbers, you are again getting a whole number because 0 is also a whole number. So here closure property under multiplication for whole numbers is actually satisfied. So now let us discuss about closure property under division for the same whole number. So closure property under division. So let us take the same example. If we take same example, we will not get the answer what we are desiring. So I will just take 1 and 2 as my example. So 1 is also a whole number, 2 is also a whole number. So when you divide 1 and 2, are you getting a whole number? You should actually check. If you are getting whole number, then closure property under division will be satisfied. If you don't get whole number, then closure property will not be satisfied for division for these whole numbers. So now 1 is also a whole number, 2 is also a whole number. So now 1 divided by 2, that means A divided by B is equal to C. So here if A is also whole number, B is also whole number, C should be whole number, then only closure property under division will be satisfied, or else closure property under division will not be satisfied. So here I am taking 1 in the place of A, 2 in the place of B. So 1 divided by 2 will be 1 by 2. So 1 by 2 is actually a fraction. 1 by 2 is actually 0.5. We are getting answer in decimal points, or we are getting answer in fraction, which is not a whole number. So when you actually divide one like whole number with a whole number, you are not getting a whole number. You are not getting a whole number. Hence, closure property under division for whole numbers will not be satisfied. So now coming to the conclusion part, closure property under addition was actually satisfied for whole numbers. Under subtraction was not satisfied for whole numbers. Under multiplication it was actually satisfied. Under division it was not satisfied. So if you consider the set of whole numbers, for closure property, addition was satisfied, multiplication was satisfied, but subtraction and divisions were not satisfied for this whole numbers for closure property. Now let us do the same experiment with integers as well. So closure property, so I'll just write closure here. So closure property for addition. So if we are considering addition, closure property under addition for integers, then whether it will actually obey the closure property of addition or not. So let us take two examples. One is minus 2 and the other is 3. So here one number is minus 2 and the other is 3. So here A plus B should be equal to C. So if A and B are integers, then C should also be an integer. So if A, B are integers, then C should also be integer after doing addition. So then only closure property of addition will be satisfied. Now let us take minus 2 and 3 as our example. So minus 2 plus 3. So in the place of A I am substituting minus 2, in the place of B I am substituting 3. So when you do minus 2 plus 3, you will get answer as 1. So even 1 is an integer. So after adding two integers, you are actually getting the integer only, because 1 is also an integer. So here you can see that closure property under addition for integers is satisfied. Similarly, if you take closure property under subtraction, then also I'll take the same example minus 2 and 3. So minus 2 comma 3. So here also minus 2 minus 3 should give you a integer itself. That is a minus b is equal to c. If a and b are integers, then after doing subtraction, the answer which you get should also be an integer. Then only closure property of subtraction will be obeyed for integers. So here in the place of a I am substituting minus 2 and in the place of b I am substituting 3. So minus 2 minus 3. So minus 2 minus 3 will be minus 5. So here minus 2 is also integer and 3 is also an integer. So after subtracting minus 2 and 3, you are actually getting minus 5 as your answer. So that is also an integer. So here you are actually getting integer only after doing subtraction. So that's why closure property under subtraction for integers will also be satisfied. So now coming to the closure property of multiplication, let us check whether integers will obey closure property under multiplication or not. So let us take the same example minus 2 and 3. So if a into b is equal to c and if a and b belongs to integer set, then the answer which you get after multiplying two integers should also be an integer. So then only closure property under multiplication for integers will be obeyed. So now let us take minus 2 as a and 3 as b. So after doing minus 2 into 3, you will get 2 into 3 is 6, minus into plus will be minus. So minus 6 is the answer. So here minus 2 and 3 are integers. So when you multiply these integers, you are again getting an integer, that is minus 6, because even minus 6 is an integer. So closure property under multiplication for integers is also satisfied. Similarly, closure property under division. So for closure property under division, we have to test for integers. So let us take the same example minus 2 and 3. So if you actually divide a and b and if you get an answer, so if you divide two integers and the answer should also be an integer, then only closure property under division will be satisfied. But let us check whether we are getting integer or not. So minus 2 is also one integer, 3 is also one integer. So in the place of a, I will substitute minus 2 and in the place of b, I will substitute 3. So minus 2 divided by 3 will be minus 2 by 3. So now you can see there is a fraction coming into the picture. So here this is not an integer. So this particular number is not an integer. So that's why when you divide two integers, you are not getting an integer. So closure property under division for integers is not satisfied. So coming to the conclusion of this particular closure property for integers, then let us go on seeing which and all was satisfied. So closure property under addition, closure property under subtraction, closure property under multiplication. All these three were actually satisfied by this integer. So I am putting tick mark for all these three. But closure property under division was not satisfied by integer. So addition, subtraction, multiplication of closure property was actually satisfied by integers, but division was not satisfied by integers. Like closure property under division was not satisfied by integers. Now we have actually tested properties for whole numbers, natural numbers and integers. Now let us test the same property, closure property, for rational numbers as well. So before going into that, you should always remember any number which is there in the form of p by q is actually known as rational number, provided that here denominator should not be equal to 0. Because if you consider any number like 3 by 0 or 4 by 0 or 6 by 0, then all these numbers are not determined. So they are not in the range of rational numbers. So that's why any number which has p by q form will be rational number, but denominator should not be 0. If denominator is 0, then that particular number is actually not determined, because you cannot divide any number with 0, because after dividing a certain object or a certain thing with 0, what you will be getting? So you will be not getting any logical sense behind this. So that's why q should not be 0. That means denominator should not be 0. Then only such particular numbers will be a rational number. So please keep this in mind. So now let us actually check what is closure property for rational numbers. So first we will check closure property under addition for this particular rational numbers. So let us take two example. One is 1 by 2 and the other is 1 by 3. So these are two rational numbers which are there in the form of p by q. So now if you are adding two rational numbers, then the answer which you get after adding two rational numbers should also be a rational number. Then only closure property under addition for rational numbers will be satisfied. So now in place of a, I'll be substituting 1 by 2 because 1 by 2 is also a rational number and 1 by 3 is also a rational number. In the place of b, I am substituting 1 by 3. So if you actually add these two, you can take LCM of 2 and 3. So 2 comma 3, the LCM of 2 comma 3 will be 2, 1, 3. So 2 into 3 will be 6. So 6 is your LCM for this particular 2 and 3. Because while doing addition, you should actually take 1 by 2 into 6. Like you should multiply that with LCM and again you should multiply this 1 by 3 also with 6. And you should divide whole this thing with LCM, that is 6. So now 2 ones are 2, 2 threes are 6, 3 ones are 3, 3 twos are 6. So now 2 into 1 is 2, 3 into 1 is 3. So now you got 3 plus 2 divided by 6. So 3 plus 2 is 5 by 6. So after adding two rational numbers, again you are getting a rational number. So that shows closure property under addition for rational numbers is also satisfied. So now let us check closure property under subtraction for this same rational numbers. So let us take the same example 1 by 2 and 1 by 3. So now let us actually subtract 1 by 2 and 1 by 3. So when you subtract two rational numbers, the answer should also be a rational number. Then only the closure property under subtraction for rational numbers will be satisfied. So now you should actually subtract 1 by 2 and 1 by 3. So 1 by 2 minus 1 by 3. Again you have to take LCM of 2 and 3. So that will be 6. So you should multiply 6 with this 1 by 2. So that will be 2 ones are 2 threes are. So you'll get 3 minus 2 divided by 6. So here I actually multiplied this 1 by 2 with 6, 1 by 3 also with 6, and same thing I am getting 3 and 2. So 3 minus 2 divided by 6. The LCM 6 you have to put in denominator. So now 3 minus 2 is 1 and in denominator 6 is there. So even after subtracting two rational numbers, you are also getting rational number as your answer. So that means even after subtraction of two rational numbers, you are getting rational numbers, shows that closure property under subtraction for rational numbers is satisfied. So now let us check closure property under multiplication for this particular rational number. I am taking the same example 1 by 2 and 1 by 3. So here also if you multiply two rational numbers, then the result which you get should also be a rational number. So when you multiply two rational numbers, the result should also be a rational number. Now 1 by 2 is one rational number, 1 by 3 is another rational number. So always while doing addition and subtraction, you should actually take the LCM of denominators and you should multiply individually with those numbers and whole you should divide by the LCM. But here when it is multiplication and division, directly you can multiply numerator and numerator and denominator. So there is no such condition of taking LCM. So I will be directly multiplying numerator and numerator. So 1 into 1 will be 1 and denominator into denominator, where it is 2 into 3. So 2 threes are 6. So 1 by 6 is the answer for 1 by 2 into 1 by 3. So 1 by 2 is also a rational number, 1 by 3 is also a rational number. When you are multiplying two rational numbers, you are again getting answer as a rational number because 1 by 6 is also a rational number. So this shows closure property under multiplication for rational numbers is also satisfied. Next let us check closure property under division. So closure property under division is also satisfied or not. Here also when you actually divide two rational numbers, you should again get a rational number. So here I am slightly changing my example. I am taking 1 by 3 as one rational number and 0 by 1 as another rational number, because here 0 is also a rational number, because 0 you can write as 0 by 1. So because just 0 can be written as 0 by 1, because 0 by 1 will again be a 0. So that's why 0 by 1 is also a rational number, but here denominator is not 0. Hence this is also a rational number. Here also denominator is not 0. Hence 1 by 3 is also a rational number. Now let me divide 1 by 3 with 0. So 1 by 3 divided by 0. So that means 1 divided by 3 into 0. So that will be 1 by 0. So any number, if it is having denominator as 0, then that particular number is not defined. So as I explained previously, denominator should not be 0. So any number which is expressed in the form of p by q will be rational numbers, but denominator, that q, should not be 0. But here after dividing 1 by 3 and 0, we are actually getting 1 by 0 as our answer. So 1 by 3 divided by 0, we are getting 1 by 0 as our answer. So after dividing two rational numbers, we are actually not getting any rational numbers. So this particular 1 by 0 is not a rational number. Hence, closure property under division for rational numbers is not satisfied. So coming to the conclusion part of closure property for rational numbers, you actually got addition, subtraction, multiplication was obeyed for rational numbers. So addition, subtraction and multiplication was actually obeyed for rational numbers for this closure property. So addition was obeyed, subtraction was obeyed, multiplication was obeyed. But division, closure property under division was not obeyed by this particular rational numbers. So addition, subtraction, multiplication is obeyed, but division, closure property under division for rational numbers is not obeyed. Next we will move to the second property, that is commutative property. So in commutative property, if you are actually considering a set, so let's say you have a set Z, like integer or whole number or natural number, any kind of set like that, then if A and B are actually interchanged, for example, if you are taking commutative property for addition, then A plus B should be equal to B plus A. Then only if this particular property is satisfied, then that particular set, like rational numbers, whole numbers or integers, will be satisfying commutative property for addition. So let us go on testing individually for whole numbers, integers and rational numbers. So first let us take whole numbers. So let us actually prove commutative property under addition for whole numbers, because if you prove for whole numbers, it will also apply for natural numbers, because natural numbers is actually contained in whole numbers as well, because in natural numbers only 0 will be absent. So in whole numbers, including natural numbers, there will be 0. So first let us test commutative property under addition for whole numbers. So let us take two examples for whole numbers. One is 0 and the other is 3. So here 0 is also a whole number, 3 is also a whole number. So commutative property for addition, you should always remember A plus B should be equal to B plus A. So if A and B are actually whole numbers, B and A is also whole numbers, but it should actually satisfy A plus B and B plus A. So even if you actually add this A and B, even after interchanging this A and B, and if you add again, the same answer should be there. Like you should get the same answer. So here 0 is one whole number, 3 is another whole number. Let us check whether this 0 and 3 will obey this particular equation or not. So 0 plus 3 is actually equal to 3. So now 3 plus 0 is also equal to 3. So here from this particular equation, let us name this as equation 1 and equation 2. So from equation 1 and equation 2, we are actually getting 0 plus 3 is equal to 3 plus 0. Because even when you do 0 plus 3, you are getting 3. Even after doing 3 plus 0, you are getting 3. So that means 0 plus 3 will be equal to 3 plus 0. So that means this particular whole numbers are satisfying this particular equation. So commutative property under addition for whole numbers is actually satisfied. Now let us actually test commutative property under subtraction for this whole numbers, whether it will be satisfied or not. So let us take the same example 0 and 3. So now a minus b should be equal to b minus a. Then only this particular commutative property under subtraction will be satisfied for that particular set of numbers. So now let us take 0 and 3 as our whole numbers and we will test whether this equation is satisfied or not. So 0 minus 3, like a minus b is there. So I will substitute a as 0 and b as 3. So 0 minus 3 will be minus 3. Whereas when you interchange this 0 and 3, it will become 3 minus 0. So 3 minus 0 is actually plus 3. So here when you do 0 minus 3, you are getting minus 3. And when you do 3 minus 0, you are actually getting plus 3. That means 0 minus 3 is not equal to 3 minus 0. So here whole numbers are not satisfying this particular equation. So this particular equation is not satisfied by this whole number. So commutative property under subtraction for whole numbers is not satisfied. Similarly, commutative property for multiplication. Let us check for multiplication. So commutative property under multiplication will take 0 and 3 as our whole numbers. So here also a into b should be equal to b into a. This is the condition which a set of numbers should obey. So if 0 and 3 are two whole numbers, then 0 into 3 will be 0. 3 into 0 is also 0. That means 0 into 3 is equal to 3 into 0. So these particular whole numbers are satisfying this a into b is equal to b into a condition. So here also commutative property under multiplication for whole numbers is also satisfied. Now let us check commutative property under division for this particular whole number. So commutative property under division. So let us take the same example 0 and 3. So let us see whether we are getting whole number or not. So here also if a divided by b should be equal to b divided by a. So if this particular condition is satisfied, then only commutative property under division is satisfied. So now 0 and 3 are two whole numbers. So 0 divided by 3 will be 0 by 3. So 0 by 3 will be 0. So now let us interchange the place of a and b. So that will be 3 divided by 0. So 3 divided by 0 is 3 by 0, which is actually not defined. So this particular number is not defined. So that's why here you are not getting the same answer when you actually interchange the position. So here a divided by b is not equal to b divided by a, because 0 divided by 3 is not equal to 3 divided by 0. Hence divisions, commutative property under division for this particular whole number is not satisfied. So coming to the conclusion for this particular commutative property for whole numbers, then commutative property under addition for this whole numbers was satisfied, subtraction was not satisfied, multiplication was actually satisfied, division was not satisfied. So commutative property under addition, subtraction, multiplication and division, if you are taking for whole numbers, then addition is satisfied, multiplication is satisfied, but for subtraction and division it is not satisfied. So now similarly you can go on testing commutative property for integers as well. So coming to the commutative property, like addition of commutative property under addition for integers, let us take two example, -1 and 3. So when you actually add -1 and 3, you are actually getting -1 plus 3 will be plus 2. So 3, when you interchange this particular position, so it will become 3 plus of -1. So 3 plus of -1 is actually 3 minus 1, which is again plus 2. So here even when you actually interchange this particular integers, that is a and b, still it will satisfy a plus b is equal to b plus a. So here you can see -1 plus 3 is equal to 3 plus of -1, which is giving the same answer 2. So that means these particular integers are satisfying this particular condition. That is -1 plus 3 is equal to 3 plus of -1. So here commutative property under addition for integers is satisfied. Similarly, testing commutative property for subtraction, let us test for this integers. So let us take the same example minus 1 and 3. So if a minus b should be equal to b minus a. So only when this condition is satisfied, then commutative property under subtraction will be satisfied for integers. So now minus 1 is one integer and 3 is another integer. So minus 1 minus 3, that is a minus b, will be equal to minus 4. Similarly, when you interchange this a and b position, then it will become 3 minus of minus 1, because here one integer a is actually interchanged, like a and b are interchanged. So in the place of a, I should write minus 1. So now this 3 is b, this minus is there, and this minus 1 is a. So here it is actually b minus a. So when you do this, it will be 3 minus of minus 1. So 3 minus of minus 1 will be 3 plus 1, because minus into minus is always plus. Should always remember, minus into minus is plus, minus divided by minus is also plus, but minus into plus is always minus, plus into minus is also minus. So you should remember this. So here minus into minus is plus, so hence 3 minus of minus 1 becomes 3 plus 1, which is actually 4. So here you can see minus 1 minus 3 is giving you minus 4, whereas 3 minus of minus 1 is actually giving plus 4. So here also you can see 1 minus 1 minus 3 is not equal to 3 minus of minus 1. That means this particular condition is not obeyed. So commutative property under subtraction for integers is not obeyed. So now let us check commutative property under multiplication for this particular integers. So let us take two integers, that is minus 1 and 3. So if a into b should be equal to b into a, only when this condition is satisfied, then commutative property under multiplication will be satisfied. So minus 1 and 3 are two integers. So minus 1 into 3, that is a into b, will be minus 3. So b into a, that is 3 into minus 1, will be again minus 3. Here it is plus 3, here it is minus 1. So plus into minus, minus 3 into 1, 3. So minus 3. Here also you are getting minus 3 as answer. Here also you are getting minus 3 as answer. That means minus 1 into 3 is actually equal to 3 into minus 1. That shows a into b is equal to b into a. So commutative property under multiplication for integers is satisfied. Similarly, if you consider commutative property for division for this particular integers, then also I'll take the same example minus 1 and 3. So if a divided by b should be equal to b divided by a, only when this condition is satisfied, then commutative property under division will be satisfied. Now I have considered two integers, that is minus 1 and 3. So minus 1 divided by 3 is equal to minus 1 by 3. So I'll just interchange the position of a and b. So now it will become 3 divided by minus 1. So here 3 divided by minus 1 will be minus 3 by 1. So here when you divide minus 1 by 3, you are getting minus 1 by 3. So when you are dividing 3 by minus 1, you are getting minus 3 by 1. So here you are getting different answer. So that shows minus 1 divided by 3 is not equal to 3 divided by minus 1. So that means a divided by b is not equal to b divided by a for integers. So commutative property under division for integers is also not satisfied. So coming to the conclusion, commutative property under addition, commutative property under subtraction, commutative property under multiplication, commutative property under division for integers. So for addition, commutative property under addition was satisfied, subtraction was not satisfied, multiplication was satisfied, division was not satisfied. So commutative property under addition, subtraction, multiplication and division for integers are as follows, like in addition and multiplication, commutative property under addition and multiplication are satisfied, but commutative property under subtraction and division are not satisfied by this particular integers. So now let us test the same commutative property for rational numbers, because the name of this chapter itself is rational numbers, so we should actually test these particular properties for rational numbers as well. I think you might have learned for whole numbers, natural numbers and all in your previous classes. So in this particular chapter we are actually discussing rational numbers. I am just revising the concepts which were actually learnt in your previous classes. So we will test this particular commutative property for addition for this particular rational numbers. So let us take two rational numbers. So 1 by 3 and 1 by 2. So these two are two rational numbers. So here also for commutative property under addition, there is a particular equation, that is a plus b should be equal to b plus a. So if both a and b are rational numbers, then a plus b should satisfy b plus a. That is a plus b should be equal to b plus a. Then only commutative property under addition for rational numbers will be satisfied. So I am taking 1 by 3 and 1 by 2 as two rational numbers as example. So let us add this 1 by 3 and 1 by 2. So 1 by 3 plus 1 by 2 will be, you should take LCM of 3 and 2, that will be 6. So into 6 will be 3 1s are 3 2s are. So 2 plus 3 divided by 6. So you'll get 5 by 6 as answer. So now if you interchange this a and b, so now it will become 1 by 2 plus 1 by 3. So here 1 by 3 plus 1 by 2 was there. Now it will become 1 by 2 plus 1 by 3. Now it will be b plus a. So again here, when you actually take LCM of 2 and 3, it will be 6. So again when you solve this, you will get 3 plus 2 by 6. So again 3 plus 2 is 5. So 5 by 6 is the answer. So when you do 1 by 3 plus 1 by 2, you are getting 5 by 6. Even after doing 1 by 2 plus 1 by 3, even after interchanging them, if you are adding them, then also you are getting 5 by 6 as your answer. So that shows 1 by 3 plus 1 by 2 is equal to 1 by 2 plus 1 by 3. That means this particular rational number is actually obeying this particular condition, that is a plus b is equal to b plus a. So here commutative property under addition for this particular rational numbers is actually satisfied. Now let us come for commutative property under subtraction for this particular rational numbers. Let us take the same example 1 by 3 and 1 by 2. Let us see whether this particular condition is satisfied or not. So the condition is a minus b should be equal to b minus a. So let us check whether this particular condition is satisfied or not. So now if I take 1 by 3 minus 1 by 2, then you should actually take LCM of 3 and 2, that will be 6. So it will be 2 minus 3 divided by 6. So 2 minus 3 by 6 will be minus 1 by 6, because 2 minus 3 is minus 1. Similarly, when you do 1 by 2 minus 1 by 3, then it will be 3 minus 2 divided by 6, because you should take LCM of 2 and 3 and you should solve accordingly. So you have learned this solving things in your previous class. So even I have showed one particular example how to add and subtract rational numbers. So 1 by 2 minus 1 by 3 will be 3 minus 2 by 6. So here you are getting 3 minus 2 as 1 and in denominator you are getting 6. So now you are getting answer 1 by 6. So when you do 1 by 3 minus 1 by 2, you are getting minus 1 by 6. But when you interchange that place, like 1 by 3 and 1 by 2, then you are getting 1 by 2 minus 1 by 3 and the answer you are getting is 1 by 6. Here minus 1 by 6 and 1 by 6 are not equal. That means 1 by 3 minus 1 by 2 is not equal to 1 by 2 minus 1 by 3. So that means here this particular a minus b is not equal to b minus a for this particular rational number. That shows commutative property under subtraction for this particular rational numbers is not satisfied. Now let us test commutative property under multiplication for this particular rational numbers. So let us take the same example 1 by 3 and 1 by 2. So condition here is a into b should be equal to b into a for commutative property under multiplication to get satisfied for rational numbers. Now let us take 1 by 3 and 1 by 2 as a and b. So 1 by 3 into 1 by 2 will be, you can directly multiply numerator and denominator. In case of multiplication and division, you can directly do that operation between numerators and denominators. Only in addition and subtraction you should take the LCM of subtraction, like the denominators, and then you should proceed further. So here 1 by 3 into 1 by 2 will be 1 into 1, 3 into 2. So it will be 1 by 6. So now if you interchange these two particular numbers and if you write it as b into a, that is 1 by 2 into 1 by 3, again it will be 1 by 6. So here you can see 1 by 3 into 1 by 2 is actually equal to 1 by 2 into 1 by 3. That means rational numbers are actually satisfying this particular condition. So commutative property under multiplication for rational numbers is also satisfied. So now let us actually discuss commutative property under division for this particular rational numbers. So commutative property under division. Let us take 1 by 3 and 1 by 2 as our example for rational numbers. Here also a divided by b should be equal to b divided by a for rational numbers to become commutative under division. Rational numbers to be satisfying commutative property under division. So now let us test whether it will satisfy or not. Because 1 by 3 divided by 1 by 2 and 1 by 2 divided by 1 by 3 should give the same answer. Here let us see whether we are getting same answer or not. So 1 by 3 divided by 1 by 2 can be written as, so in the case of rational numbers, you can actually change this division symbol into multiplication symbol by interchanging numerator and denominator of the number which is there after that particular division symbol can be interchanged. The numerator and denominator of that particular number should be interchanged. So here I am changing this division into multiplication by interchanging numerator and denominator of the number which is there after this division symbol. So here 1 by 3 divided by 1 by 2 will become 1 by 3 into 2 by 1. So now you can see division has changed to multiplication and the number which is after that division symbol is also interchanged, like the numerator and denominator of that number is interchanged. So 1 by 2 has become 2 by 1. Now you can easily solve this. So 2 into 1, numerator into numerator, that is 2 into 1 is 2, 3 into 1 is 3. So 2 by 3. So when you divide 1 by 3 by 1 by 2, that is 1 by 3 divided by 1 by 2, you will get answer as 2 by 3. Now if you interchange this a and b position, then it will be 1 by 2 divided by 1 by 3. So again you will actually change this to multiplication symbol and you will interchange the numerator and denominator of this particular number which is there after this division symbol. So that is 3 by 1. So again you are actually getting the answer as 3 into 1 as 3, 2 into 1 as 2. So here you are getting 2 by 3 as your answer. Here you are getting 3 by 2 as your answer. That means 1 by 3 divided by 1 by 2 is not equal to 1 by 2 divided by 1 by 3. That means here a divided by b is not equal to b divided by a for rational numbers. So that shows commutative property under division for rational numbers is not satisfied. So coming to the conclusion of this particular commutative property for rational numbers, then commutative property under addition for this particular rational numbers is satisfied. Subtraction, commutative property under subtraction for this rational number is not satisfied. Commutative property under multiplication for this particular rational number is satisfied. Division for this particular commutative property for rational numbers, commutative property under division for this rational numbers is not satisfied. So this was the part 1 video of this particular rational numbers chapter. So the continuation of this part, like the continuation of this particular rational numbers chapter will be there in part 2. So please do watch this part 1 video of rational numbers and also watch the part 2 video of this particular rational numbers. So like this, I will be uploading more and more physics, chemistry and mathematics videos in this particular YouTube channel starting from 8th standard till 12th standard. So if you want to learn physics, chemistry and mathematics, then please do subscribe to my channel and stay tuned with my channel. Thank you.